So today it's a Halloween day, 31st of October, class number 23, and actually it is consistent. We have a Halloween party for structural dynamics after this one. Okay, so you have 3 hours structural dynamics today. Anyway, it doesn't relate to anything about this class. Last time we used the geometric stiffness matrix. I showed you how to use it to determine the buckling load. That's the Eigen buckling or bifurcation problem that you can find just one root of the root of solution, not necessary to be just one. But basically, the buckling load will be controlled by the first Eigen value, which is the lowest, because you load up, you meet the lowest one, and then your system just fails. So if you plot between the deformation of your structure versus the load, you don't find any deformation until the load reach the buckling, and then you get the infinite deformation. That is the loss of stability. The thing is that that situation generally is for the situation where you have just the load alone with a single column, probably, or even for the frame. But in the frame case, you could have something that look like this. You have many columns, you have beam, etc., etc. You have something prevent the sway, but still the load that you have is concentric to the column. So there is no issue about how much load is distributed to each individual column. So the situation like this, you can have a precise, maybe the prescribed fraction of the load on each individual column. Last time we cover up to the frame problem, right? But just one beam and one column. So maybe we can start with this one, but I will also talk about the next problem as well. The height 1, 2, 3, 4, 5, 6, right? Okay. And then we have 2, 4, 5. Okay. And this one likewise, I make it the frame, and I can drop in something special like put the hinge just right here. And then now put the load. At 2 different points, you might have different load magnitude. So I will just put something like here. Let's say this is 3p, and this is 5p. Okay. And let us give the dimension to our structure. So our frame, we have the column of which the height is equal to 6L, and this is 5L. Same height, Doesn't look fun to me. Okay. Okay. Make it like this. So this side is for L. Beam was supposed to be, let's say, 8 EI, whereas the columns are, first one is basic, just EI, and this one is 3 EI. You apply the load to this system, you do not cause any deformation. Well, you might say that axial deformation will be there, but you will not cause any lateral deformations. Okay, so structure just look intact. So you don't see anything until you reach the buckling load, and then suddenly you have the structure collapse down on the floor. We would like to find the P, which is going to be in terms of EI and L. We will set up the stiffness matrix of this system. Let me give just to make sure that we understand this. You know that it is a hinge. But the second problem will be totally different. So the case like this, where you only have the load, concentric load through the column, is quite rare. In reality, you apply the load on the beam, on the slab transfer the load to the column, and basically at the first round of the analysis, you do not have the predetermined internal axial force in each individual column. So let's take a look at the second case. So I think I can just copy the picture we have for the first one. No. So let's make problem number 2 just identical to problem number 1 in the structure, okay? But the difference will be the load. So we will apply load in a different manner. Just make it a distributed load. If you have the load like this, you have no idea left column how much and how much on the right column. So you need to do the iterative solution. Maybe this is the best way because we can share the same structure, so we don't need to cast the stiffness matrix for the whole structure, okay, too many times. Use of geometric stiffness matrix, we need to enable the deformation. We need to enable to be able to pick up the deformation which is caused by the second order moment. Okay, so in the column if, well, for this case, we don't know if it's going to lose the stability in which mode, sway mode, or the like the pin column buckling. Okay, you don't know how it's gonna look like. What I mean by the sway mode, it might just go like this. So if it buckle, it loses stability in the sway mode like this. The nodal point prepare at the top of column surface, right? That is enough to capture the large deformation effect from the second order moment. But if it doesn't go like this, if, well, the stability of the frame is not that bad, it goes like this, which is also possible. Then these points are not captured. The large deformation here is not addressed by the way we set up the degree of freedom. So to make sure that we will not end up with a situation like this, better put the node there to make sure that we at least pick up the second order moment effect. So I will use the, what color? Maybe this one. So I'll make the midpoint discretization in the column. I don't think I need to do that in the beam. For the beam, as you can see, we do not expect any second order effect. It's not likely in the beam. Generally the beam is larger in the EI value, so the stability will not be the case. Well, for the short building, for the tall building, your column will be, the EI for the column will be large in comparison with the beam anyway. But for typical low-rise short building, we get a very large EI for a beam compared to column. Okay. So we have the midpoint discretization. So we have two elements for column on the left and likewise for the right one. In total we have 5 elements. Let me name the element. So element number 1, 2, number 3, number 4, number 5. Maybe I should just define the degree of freedom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. First of all, we have to prepare the setup for the geometric stiffness matrix. So you look at this here. I have the infrastructure which is made quite easily like so. So P is given in terms of EI over L square. So later on, when you plug in the P into the geometric stiffness matrix, you push the P, it is P over L multiplied by things inside, right? So we push the L inside and then we arrange the equations. Force equation we multiply by L throughout to make it the moment equation, and then we take the, we manipulate a little bit with the variables. So you have the variables in the same unit rather than just the length scale and the radian scale. Okay, so we do all of that. We come up with this setup. EI for each individual element will be given in terms of the number multiplied by the EI okay, EI like a universal EI. Length for this element is equals to, okay, how well that depends, okay, the scale multiplied by L. So this is the linear stiffness matrix, which is made of 12 EI over L cube and so on and so forth. I will not explain in detail. 6 EI over L square. All of these are in here. If you just plug in 1 and 1, then you will see the 12, 6, minus 12, okay, etc. Right? And likewise for a P, if the P effect is so small, then you'll be having this part has not been multiplied by the P yet, so it will appear later on in here as a combined stiffness matrix. Okay, so I delete this first. So in order to combine it, it has to be this value minus the P, right? Multiply by this part, and the P has to be the log cell, so it doesn't move. Okay, it go like this and copy down. Okay, so if you increase the value of the P, you start seeing the effect. All right, but over here, this one is the stiffness matrix of it's a local stiffness matrix, okay, of that individual element. So in order to make it easy for us to do the plugging into to combine the stiffnesses from many elements, we will prepare the space which is the matrix, the K system for the whole problem, and this contains degree of freedom from 1 to 19. So we're gonna keep 1, 3, 4, 6, 7, 9. Okay, the 7 and 10 will be the same, right, if the member are axially rigid. So you will not expect any relative deformation and displacement between 7 and 10. So you keep just 7. 11 will be useless. You keep 12 and 13. 15 is useless. 14 is real. 16 is going to be there. And then, okay, 17, 19. Okay, for 18, you will find it out from the equilibrium equation that governs this beam. So we keep how many? Let's count. If we don't keep these 2 degrees of freedom, it will not show up. So you don't keep the number 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, much smaller size. Let's see. So if this is the starting node and this is the ending node for element number 1, then the local degree of freedom is associated with the global DOF 4, the first one. The second one is number 6 and 1 and 3. 4, 6, 1, 3. Okay, so I note it 4, 6, 1, 3 like this. 4, 6, 1, 3. So it's going to be a little hectic, right? 4 is equal to this. 4, 6. It is this one. 1, 3. 1 and 3. 4, 6, 1, 3. As next row, this, and this one, right? And then row number 1, column 4, this, row 1, column 6, row 1, column 1, and row 3 column 1, row 1 column 3. Last one. This 4 6 1 3. Just look roughly if there is anything wrong. If the matrix is not symmetry, then something must go wrong. That's the easiest way to check. So this is symmetric, this is symmetric, this is okay, this is okay, this is okay, okay. Alright, then we have all this stuff in. This is for the element number 1, which is tied up with the parameter we input over here. We got to have to change that EI, right? We haven't done that. We will go seek for this one. Okay, so just assume the 0 first. The EI is 3 EI, the length is 3 L, so you drop in the 3 and the 3. Okay, done. Now element number 2. Element number 2, the load P has to be the same as here, so you do not have to touch this one. The EI 3, the L is also 3, but this one has to be modified a little bit, so no fill, and we zero them all out. This one, if the starting node is on the top, ending node is here, right? The local DOF align well with the global DOF. 7946. So 7946, 7946. All right. 7 and 7, 7, 9, 4, 6, right? And then this is row number 9, right? 7, 9, 4, and 6. Next one, this is number, no, okay, you got to jump up. 7, oops, 9 here, 4, and 6. Last one, 7, row number 6, okay, 9, row number 6, 4, 6. Okay, color it up and see. 2 symmetry, 1 3 3 2 2 2 2 2 1. Okay, yeah, looks good, looks perfect. So let's move to the element number 3. Element number 3, the load will be 0, 8 EI and 5 L. Okay, so here I put the 0. We will not have anything. Let us clear this out, and then we'll be able to fix things up. So this involves 8, we don't keep it anymore, right? So we have just 9 and 12. Okay, for this beam, DOF 9 and DOF 12, the vertical degree of freedom are not counted in. If you want to count in, then we got to come back and use the program over the trips, and it is a good thing to bring the laptop when we wait for the plane to taxi off the runway. They can write a lot of code. So probably on Tuesday we'll be able to come back again. I just finished the input file line by line. Okay, just check and got the command. So the input will be from the text file. Okay, in the last class we don't have that much time, and yeah. And then okay, we fix the bug and we make use of the the Octave, the M file. Okay, for the analysis, even for we can extend it for the geometric stiffness metric coding. All right, so 9 and 12. 9 is here, 12 is here. So we keep 9 and 9. 9 is here, right? 9, 12, 12, 9, oops, okay, yeah, and 12, 12, that's it. Done with the beam. Move to the column. Element number 4. Element number 4, let's take a look here. If this is 5p, this is a fraction of 3 to 5, right? The load ratio is 3 to 5. So you multiply by 3 over 5 of this one in order to get this one. So we come here, and this is equal to 0.6 multiplied by element number 1, right? So if the element number 1 you put the 5 in, then you get the 3 for element number 4. Okay, just tie them up. And the EI is equal to 1, EI ratio, and the length is 2. So 2, and here's 1. That's it. And let's check for a degree of freedom. Number 10 is actually number 7. So we have the 7, 13, 14, 16. Okay, you are following me, right? 7 is equal to 10. So 7, 13, 14, 16. 7, 13, 14, 16. Yeah? 7, 13, 14. So take a look. 7 and 7 is right here. 7, 13, 14, 16. Then I copy. Okay. Next, 13, right? 13, 13, 7 is this one. 13, 7. Basically, you can copy it down like this. And this is 13, 13. So, boop, boop. Right. Okay. Next one. Element number 5. This one is given by C39. What is the C39? No, okay. So I'll make it equal to number 4. Okay. Seems to be better. Okay. Alright. Same, right? For number 4. Just different way to plug in. So I clear this node out, and I'll look at the number 5. We have 14, 16, 17, 19. 14, 16, 17, 19. There you go. 14, 16, 17, 19. Oh, well, seems to be lucky, right? Easy one. 14, 16, 17, 19, and copy down. That's it. Okay, we get everything, then we can combine them into one stiffness matrix. Actually, I don't really have to keep the support degree of freedom, but okay, next problem I'm gonna need it. 0 first, okay, and then we have this add up with this one and add up with this one and add up with this one and add it up with this one, the last one. Okay, I got that, and copy and copy. Actually, if you don't want to, you can do the conditional formatting if you yeah, you can see which one is non-zero. Yeah. Okay, yeah, this one looks okay. Looks good. I think the matrix looks like it is. We have a good symmetry in here. Okay. Now, what do we need to keep? We don't want the DOF 1, 3, 17, 19 as they are the boundary conditions, right? 1, 3, 17, 19. 1, 3, 17, 19. Okay, so basically we will just consider this part in here. Can you see clearly? The part in the thick line in here, we discard the 1, 3, and 17, 19 DOF and rows out of the consideration. So we take care of, we just need to care about this. I will just, okay, conditional doesn't work. Can I clear it? Can I clear rules? Yeah, clear rules. Clear from selected cell. Where? Clear rules from selected cell. Okay, so we need the determinant of this part. So determinant is equals to MD term of this, close the bracket, there you go. We need the determinant to be 0. So with data, we what if we go seek, we say determinant has to be 0. How do we get it? We will change the cell, and it is this only cell. So as this cell change, then it ties up with the rest of the axial force on other elements. Let's check. Go seek, get the 0, and then by changing which cell, .471. Okay, .471 0.471 is compare with which one here? This one is the lowest for this one is a cantilever column for the left column, buckling load for cantilever column. This is the buckling load if it is pin, and this is what we get, 0.47, okay, due to that restraint in the middle. This is on the right hand side column. The right hand side column is 60%, the load is 60% of the left hand side column, so it is equals to 0.28. If you look at the left hand side column, let's check the pi square times EI, which is equal to 1 divided by L, which is 4 square. So that's a 16. That's the upper bound value that is possible for the right hand side, whereas the lower bound will be associated with the cantilever column case, right? So it is the pi square multiplied by EI, which is equal to 1 divided by 2 times 4 square, which is 0.1 something, okay. If we put it this way, yeah, you will see. Okay, so this is just to check with the upper bound and lower bound value, that should be, yeah, gives you the make sense number. Now problem number 2, then, okay, I have to fix the number 3 also, right, in here. Number 3 is also tied up with that, so make it C75. So if it is like 5, then it change with this one, okay, so it looks good. How about other elements? Still good or not? We fix it already, okay. For other elements, it's fixed already. So right now, the formula is tied up in a different way. We have the distribution of the load P and P, okay, on both sides. And then what if go seek, and then we were supposed to get 0 by changing this cell, okay. So it turns out to be 0.353. 0.353, this case you get 0.47 in comparison with this case. So what is that? You initially, the first case, we distribute the load on the column where the column is stronger, right? If you see the buckling load of the column, okay, you can just see that the left column actually it is stronger. Left and right column are tied up with the same beam, so that means the head displacement is controlled, okay, together. Well, the left column has some advantage that the rotation is also restrained, whereas the right column does not have any restraint in rotation, but it has the restraining effect to the left column in the, well, how to say, horizontal displacement restraining. Okay, so if you put the load magnitude distribution on the left more than on the right, you get the better deal. Better deal that I'm talking about is the larger load carrying capacity of the whole beam, whole frame system, right? If you put the P and P equally, then the buckling will supposed to occur in the right hand side column first, because this one is the weaker one and the stability issue occur in this one first. If you can maintain two columns and make them collapse at pretty much the same time, then you fully utilize your structure. That's the thing. But the point is that the way you distribute the load will change the overall frame eigen buckling capacity. All right. So it is not associated with just the structure, but it is also associated with the load pattern. But if, just in case, if the load pattern is, well, the pattern makes some sort of very clear failure mechanism on a local element. For example, if you put a lot of load in this right hand side column, very large load and very small load on the left hand side, you might change the distribution, but you will not see that the buckling load is sensitive, or it's changing much with the change of the load. Because if you put the load, the most of the load on the part that control, on the weak member that control the first failure, then if you just change this distribution not that much, then you will not see the change of the overall buckling load. Okay, so you can do more, alright? If you wish to change whatever the distribution, you can play around, but you cannot have the lateral load applying over here in order to use the eigen buckling analysis. If you apply the lateral load, then it's no longer eigenvalue, because your force vector will turns out to be non-zero, right? So it is not bifurcation problem anymore. Your structure will sway before it buckle. For eigen buckling, as you have zero force vector, your structure doesn't deform at all. So deformation remains zero until it reaches the buckling load, and then the whole frame just go. And the deformation is not, well, we cannot determine that deformation. Okay, so let's take a look at the case like that. I can just copy this. Problem number 3. Number 3 is put down here. Well, for the number 3, it does not need to be iterative solution. It doesn't have to be. You might have just a little swing of the axial force of these two columns a little bit as you apply the load. So let's take a look. We put the shape in like this. Okay. So put some load in. So right now, you cannot just find the determinant and find the buckling load. So if we cannot do such thing, how do we find out the buckling load of the system? We will plot the deformation versus the axial load like before. Deformation versus axial load, the x-axis will be the deformation I think I used to plot you the bifurcation problem response. So x-axis is the deformation, and the deformation that is sensitive. We will plot in one problem. You have so many deformation, right? You have rotation here, displacement here, vertical displacement here, and so on and so forth. But what would you pick up? We will pick up the location where it is sensitive to the buckling, and that location will be on the DOF number 7 or on the DOF 10. So if the system buckle, this place is going to move a lot, and the maximum displacement is expected over here. So x-axis denotes the displacement, and the y-axis denotes the value of the P. Well, we will keep the ratio of the P of the load on 2 columns to like 5 to 3 like this, and then we plot only P. So if we get the load in this one here equal to this number, then we divide out by 5, and then we just plot the P. So keep the P like the universal unit. Okay. Then you start with the small load. Apply small load. You run the analysis, and then you get the displacement response versus the load. You make the load into many small steps. So just keep increasing the load. Okay. So small increment, small increment, small increment, until you can see the softening of your structure. Basically, if you apply the load versus the displacement, you will expect what? The slope, what is it? It is pretty much like a stiffness. One axis is the load, one axis is the displacement. So the slope is the load divided by the displacement. It gives you the sense of stiffness. But if you have the linear elastic structure, or you don't have much effects from the second order effect, second order moment, you will expect a straight line, more or less like straight line. But once the second order moment works, once it is active, once the structure is about to lose stability, what happens is that your stiffness, your slope decreases. So you used to have the line just coming up like pretty much like a straight line. It might not be a perfectly straight line, right? But it looks pretty much like straight line. And then at one point, the slope just change, it just reduce. So that is the softening effect. You have the reduction of slope. And then at one point, you keep running the analysis, you can find that the deformation is really large, too large. And that moment is the point where we define the structure is under the buckling failure. Okay. If you keep running the analysis, you might be able to get more and more and more displacement, more and more load. Okay. But the load will be approaching to one value, which is controlled by the Eigen buckling load. Okay. So let's try this one together. We can put this load, and it should be given in the fraction of the P. So may I just make it something (0.1 P). Actually, it is a good exercise. Well, the behavior of the system will it depends on this magnitude of the horizontal load. This is the deformation U, this is the load P. Okay, I told you that you might end up with the situation like this. And the magnitude of the horizontal force that is applied, I first start with the 0.1 P. If we vary it to 0.5 or 1 P, you'll be ending up with the different curves. So the curve might look like this. If your P is larger, horizontal force is larger. Or it could be like this if your horizontal force is smaller. So the curve tends to go like to this side if the horizontal force is larger. If it is really small, you are approaching to the case where you have the Eigen buckling. Alright? And then everything will be controlled by the Eigen buckling curve. So you cannot have this line just go up through the load that is controlled by Eigen buckling. And here is the number 3. So number 3 looks like number 1, but this is the, you have to apply disturbance to your structure. So let's start. Stiffness matrix is there already. This degree of freedom is number 7. I don't care about determinant anymore. So basically I set up the force vector. And our force vector has nothing but the DOF number 7, which is this line here. And the magnitude of this is 0.1. So this is equal to 0.1 times the P, which is this one. Apply to the right hand side. So if we want to come up with the solution to this problem, maybe first of all I need to reduce the load, because over 0.471 it is the buckling, and basically we will get some ugly solution. So we start with if I can predetermine that the buckling load is about 0.47, then I make the load increment to be somewhere around 10%. So 0.05, yeah. And then when I am close to the buckling, then I need to make the step smaller and smaller. It is pretty much like the load testing. So when you are quite close to the failure load of your structure, you don't need to apply a large the large load increment. So we have this U1, U3. Okay, they are useless, right? The boundary conditions. Okay, so we don't incorporate them in there. And here is the MMULT of M inverse of this, just this matrix, stiffness matrix, multiplied by the force vector, and you have nothing more than just horizontal load apply in this one here. The sensitive is the sensitive DOF is this one, 0.316. And then actually if we want to check if this converge already or not, why do we need to check a little bit? Because once the structure deform, this deformation causes the rotation at the beam, okay, and rotation of the beam, you will have the shear which is associated with the rotation of the beam. So we will have to check by going back up here for the element number 3. You have this stiffness matrix like this. So should I just copy first and paste over here? The degree of freedom here and there is useless, right? They are 0, so I delete and I make the stiffness matrix a little smaller. This is associated with 9 and this is 12. If we apply the solution for U9 and U12, so I will put them here, U9 and U12. U9 is this one, okay, and U12 come back down again, U12, oh my eyes, so this is a displacement solution we just solved. Multiply by this stiffness matrix. For this case, you don't have the fixed end reaction, so you can find the shear force that is acting on these two member, this member, the beam member. Okay, so that is equal to this one, which is equal to MMULT matrix multiplication of this and this. Oops. I just forgot. MMULT of this and this one, close the bracket, shift control enter. Okay, what is this? Zero moment. Well, we're supposed to have this, right? You should have zero moment because we have the hinge condition at the right end of the beam. We have the shear force that is this one minus, which is going downward, right? You push the system, system sway to the side, okay, and then what? Sway to the side, but the deformed shape is like this, going down or going up. Let me see. Let me check the rotation. This is a rotation number 7, 8, 9, right? Rotation number 9. Rotation number 9 is this one. Minus is going clockwise. Rotation is clockwise. Clockwise rotation means the beam is going like this. I just draw freehand shape. Is it a freehand? Free form. So it should be, sorry, like pretty much like this, right? Okay, that end is not restrained. Okay, right. So negative means the reaction, let me draw. The reaction is going to the minus y side. So here is your beam. You have no moment. Over here, this is the shear force that is acting on your beam on the left side, and on the right side it goes up like that. That means when you consider the column which is below the beam, okay, column is here. On the column, the load will be acting like this. Okay, equilibrium. What acts on the beam like this? Okay, will act on the column on the opposite side. The beam feel that it is anchored down, so the column feel that it is pulled up, right? Gets pulled up. You push your structure to the right hand side, then overturning moment will pull the column upward. All right. The issue is that you will have the additional axial force coming in to your column. This one will reduce your column axial force, and this one will increase the right hand side column axial force. So we can do some correction. It could be the iterative solution for now. So make this correction. You add this amount to the column on the left hand side. Okay. So this one, and then minus, oops, what, okay, it shouldn't, I have to manually add this to that cell that we input. Seems like we are making a loop. This thing is calculated from that cell. So Excel sends that, and that's what you get previously. It gives another number. So 0.0022. I just add, it has to be minus 0.0022. It is the pull up force, so that makes the compression, that reduces the compression, equals to this minus 0.0022. So it reduced, whereas for number 4 and this was supposed to be 0.3, right? Initially it is 0.5 multiplied by 0.6, so you get 0.3, and then you add this up with 0.0022. Okay, so now okay, 4 and 5 are adjusted, 1 is also adjusted, 1 and 2 are also adjusted. What we have over here, we have the deformation. Oh, gets magnified 0.0642. Why is it so sensitive like that? You just change axial force, not that much. Anything change with this? Let's check. I don't want to end up with any error. 0.03. Oh no. That was 0.003, right? Huh? Right? Yeah. Almost. Okay. So you have this instead. Previously, displacement is 0.0316 at DOF 7, and next time we get the reduced displacement because the effects from the horizontal load decrease the axial force in the left side, which is subjected to higher axial load. So turns out that this horizontal force help a little bit for now. You come back and look at the force here. It doesn't change much. It used to be 0.0022. Now it turns out to be 0.0021. Okay, it is not changing much. So it is just a fraction of change. Then you don't need to continue the iterative solution. So basically we can put the conclusion in here that if the P magnitude is 0.05, this is the applied P, okay? But the final axial force in the column was corrected. So that's another thing. But we put the applied P in here. You say that in the column you don't see the 0.05, you get 0.048. That is the 0.05 P that it was applied and then gets the iterative solution corrected and turns out to be this one. Okay, and then the one that we will monitor turns to be the U7, and our U7 is somewhere around this 0.302. So we keep just a number. Next step, we increase the load to 0.1. So we change to 0.1. We come back and see. Again, you need to put the 0.1 in here and number 4, this is 0.06, right? 0.6 times 0.1, 0.06. And then when you get the displacement solution, which is 0.7 something, you come back to your beam and your beam say that, hey, I have this change 0.005 that was supposed to be applied on the column. So 0.005 here, let me, okay, 005, just 005. So let me do some sort of correction. So it's equal to 0.01 minus 0.005, 005. Okay. Over here, element number 4, 0.006 plus 0.005. You get the new set of solution. Turns out to be 0.683 for the U7. We plug in the U9 and U12 into the beam, and we end up with 0.0048. If you want, you can continue to refine the solution. So I just show it. So instead of this, then I get the 48. Apply that 48 in there, and also the 48 in element number 4. And look at the solution. Okay, I don't remember the number. It should change just a little bit. We'll come back to this point here. 48 doesn't change. Actually, maybe the latter decimal place might change, but it's just a little bit. So we are pretty happy with this solution. If we are happy with this solution, then I copy 0.684 and paste in here. Right? Continue to 0.15. You change the load, and first 0.15, that's gonna make what? 0.9, right? 0.09 in the right column. You get number here, you get the reaction there. 0.0863. Okay, I correct the axial force to be minus 0.00863, and then I'm gonna add 0.00863 down here, plus 0.00863. Okay, and then I look at the force. 86 turned out to be 8 to 1. So I come back and change it to 8 to 1. And again 8 to 1. And look at the force. 8 to 3. Well, if you want, go ahead. But this is just a fraction. Number 4, 8 to 3. Swing a little bit. Okay, 8 to 3 doesn't make any significant change. It is like 1 in 8,000 something. Okay, small enough. It approximately 10 to the minus 4 to 10 to the minus 5, right? So we have the converged solution. We pick up the number, we put it in the summary over here. Actually, if you want to track, you insert and you put the curve like this. Okay, so keep going. It looks still look good. I think I can jump to point. It buckle at where? 0.5, right? Let me go to 0.3. 0.3. 0.3. Okay, let me just do it this way. 0.3. And number 4 is also 0.3 multiplied by 1/8, right? Okay, and we will put the correction, which is 0.0318 minus 0.0318 minus 0.0318. Oh, this one is plus. Thank you. Oh. Okay. And then not 318F, it is 303. 303. Oh, actually, I think, yeah, 0.303. 3037. I think I can make it something like this. This is what? 0.3, right? And this is 0.03 what? 303. And then I make this is equals to this minus this. Okay. And number 4, make it equal to 0.6 times this one, right? And then plus this one. Okay. Okay. Yeah, so it's gonna be faster to just fill in. Where is my 0.304? Okay, let's see. 0.30, yeah, 36, 304. Okay, good enough. Then just copy this 0.44. Okay. Hardening? I don't think so. Maybe the first few iteration we just use one step. 0.4. So we come up, put the 0 here, put the 0.4 there. Okay. And then get this number 0.1006. 0.1006, and then come down. I will make the code in this way to make it faster. I don't want to come up and come down. Okay. So I just need to manually input the value. So, right? 0.11. Okay. So 0.14425. Hey, oh, it is still changing. What is that? Is that one changing in the proper way? 38. It is correct. 0.6 multiplied by E3 plus E4. Why is it? Let's see, 0.3 again. 0.3, and if this is 0, and then we put the 0.0318, it turns out to be, and then 0.3029, and then okay, 0.3037. Okay, yeah, it is working for this one. So 0.4, is it going to buckle soon? Let's check. Then 0.32, and put this 0 first. So we need to correct by 0.0383, and then we correct by 0.03682. Okay, looks good. and I am so lazy again. I copy that up here. I don't want to scroll up and down anymore. Okay, this is the solution. So this is for solution for 0.32. 0.32. Vertical axis is load. Is that right? No. Switch the x-axis switch with the y-axis. Alright. Yeah. So now your system is about to buckle. You can start seeing the softening. That may be the reason why we cannot get the converge solution at 0.4. So now try 0.35. I'm not so sure if it's gonna be possible. 0.052 or 7. 0.05172. Yeah, and add the 4 in there. Great. Still converge. This is 0.35. 0.35. Hey, we were supposed to. Okay. 0.35. Okay, gets less steep. So 0.37, and make this 0 first. 0.0657, 0.069 or 6. 0.693 still converge. Okay, yeah, you just don't need to be that crazy. Okay, 0.37 and 1. When you find it very difficult to converge, to get the convergence. So 0.39, maybe you can stop around here. 0.086. You can see now it jumps. It was supposed to be 0.104. But still manageable. When it is closer, then it will not be manageable. Okay. So for the nonlinear problem, okay, I think it is acceptable for this one. Maybe it could be the last point, 0.39. Well, if you want to push the limit, the 0.4 doesn't work, right? We saw that. If we zero this off, if you put the 0.1 in there, then it's a 0.14, 0.14 in there, it's a 0.2, okay, it's a point, it doesn't stop. Now it is 2.7. So the more you iterate, it is running away from you. If you try 0.395 and zero this, 0.093. Okay, I don't know if we can chase this one. It might be 39. Oh, still running away. 0.16. Okay, it is running away from me now. 199. Okay, it doesn't stop. So if it is not possible to converge, yes, you are in trouble. Maybe I just give you a few more points on top here to make this curve like looks better. So 0.01, 0 here, and okay, whoops. Okay, 555. We drop in there. 0.01 and then 0.03, just another point, and the curve will be perfect. 0 here, 0.03, 0.00127, okay, 122, 124, nice. And then draw the curve. Okay, so basically if you draw the straight line from the origin and tangent up, that is the linear stiffness of this structure. I can draw it like pretty much like this. So the response of your structure, if we don't consider the second order effect, you get this line. But as we consider second order effect, you get these nonlinearities coming out. So yeah, at one point here, it will buckle. The buckling load is determined. So we will say that okay, it is somewhere around this line. Will not be as much as the Eigen buckling load. So I will give you this spreadsheet for you to do homework. So the homework will include, actually you don't need this one, I delete this one out. You just need to keep the problem tree _2. Okay, so things in here, I just made the infrastructure for you to play around. So change from 0.1 to 0.03, okay, and then plot out this load deformation. You plot it along with this line, so don't discard this line I just made for 0.1. Okay, you made 0.03, 0.07, 2 lines already, and then 0.15 and 0.2. Okay, so you will make 4 lines more. Right? It doesn't take time. I made infrastructure for you already. You don't really, if you want, you make one new spreadsheet. That will be good for you, good for yourself. But this one will be given, so you can learn from it. Just in case if you get stuck, you can learn from it. But the best way to do all the things, at least this cover up your knowledge in the first part before the midterm exam, to be able to construct the stiffness matrix of everything, and then you incorporate the geometric stiffness, and then you run this iterative solution until you get the nicely converged solution, and then you plot the corresponding displacement to one set of load. Okay, and then whoop. Okay, I did it. Just Is it multiply? No. Okay, yeah, okay, it is well. It's just not confused, just worry. If I multiply this, okay, 0.1 multiplied by that, so yeah, the scale is good already. Right? So you'll be seeing the lines that I sketch for you. The higher the lateral load, the worse the buckling load you will get. The curve will be pretty much like this, whereas the sharp curve will be obtained when your horizontal load magnitude is kept small. So it will behave pretty much like the structure without the horizontal load. So it is pretty much like the Eigen buckling case. Okay. So the lowest one is 0.2 p. Point what? Point what? 0.2. 0.3. 0.3. Can you make it just 0.01? Just 0.01. Try to make it really, really small. And 4 cases, right? One last case. Just disable the effects from the second order effect, or let's say disable the P delta geometric stiffness matrix. If you disable that, what will you get? You better get this line. Okay, so try that as well. Without nonlinearities, you should get the straight line response. Q out that, and it is quite easy to Q out. You just modify the code a little bit, and then you will just Q out, and you don't need to iterate the solution, okay? Because there's no point to do so. The iterative solution affect only the nonlinear solution, because nonlinear solution depends on your presence of the axial force in the member. But if you do the linear solution without the consideration of the second order moment, well, no matter what P is, it doesn't affect the stiffness of your member, right? So you do not have to iterate. So just linear, just change the value, horizontal load value, and you'll be getting the straight line solution pretty much like this. It should be like the tangent slope of the curve. Okay, that should be just enough.